Okay, I'm hoping to get through all of the 3.2 alternate examples here in one Edpuzzle session, but there are a lot of moving pieces to this. I did go over the concept of R squared previously in the Understanding R squared assignment, so hopefully that helps us to be able to move through some of these concepts in one sitting here. But the first example, I don't know if anybody does this, but I definitely do this every time I open up a can of soda, or I always tap on it. I don't know where I learned that or who showed me that, but that makes it less likely, especially in my house. I have 3 kids. No idea who may have tampered with those soda cans before we open them. So I always give it a little tap. So these 2 AP students did an experiment. They had some cans where they didn't tap at all, some they tapped for 4 seconds, some for 8 seconds and 12 seconds, and so on. And then they measured the amount of soda that was left after the explosion. So you can see in general, amount of soda remaining, it seems like the longer they tap for, it seems like generally there's a higher amount of soda remaining. The other thing I find interesting here that I like to point out is that you have a step feature to this graph. If you take pre-calculus or even calculus and you study the greatest integer function, it's that step function. This is a great example of where you would see that. If you plotted something like AP statistics exam scores versus GPA, you would see a step feature because you can only get a 0, a 1, a 2, or a 3, a 4, or a 5 on that exam. So this is a case where we see a step feature, but we can still use a regression line to predict patterns that we might see in the behavior of the data. So they notice you're going to have 0 repeating many, many times for these different amounts, and so on with 4 and 8 and 12. And that's okay. So they have their regression line computed, and the one thing that I would like to add to this, always want to make sure that you put that hat symbol over top of whatever your X or Y variable. It allows us to differentiate between a predicted value and an actual value. What I mean by that is, if I'm on the line here, that's a predicted value, right, for the amount of soda. An actual value would be the Y value that lives up here, or this Y value. Okay, in this case, there's several of them. So we always want to differentiate between predicted and actual, and in statistics we use the little hat symbol over that. So identify the slope. The slope is 2.63. We can see that. A lot of times my students will easily identify the slope and the y-intercept, but they miss this part, interpret each. Okay, so that's what I really want to focus on. How do we interpret those? Okay, and the slope, it always has to be interpreted just like it would be in algebra as a rate of change. Okay, but it's a rate of change in the predicted value of the soda, okay, based on an increase in tapping time. So for instance, the slope of 2.63 means that for each additional second of tapping time, the predicted amount of soda is going to increase by 2.63 milliliters. We want to make sure that we use the word predicted. If I say something like, for each increase of 1 second in tapping time, the amount of soda increases by 2.6 milliliters, that 2.63 milliliters, that's sort of incorrect because this slope only has to do with predicted values, not with actual values. It doesn't affect what's happening with the actual values. It's a predicted amount. So it's really important to say something like that. On average, as tapping time increases, the amount of soda increases by 2.63. Some kind of language like that. You want to make sure it doesn't sound like you're saying that the amount of soda increases for every second of tapping. It's not exactly working that way. Okay, so notice that I use the word predicted here to differentiate, and then I do it again here for the y-intercept. For the y-intercept, which is 248.6, that's the predicted amount of soda if we don't tap the can at all. A lot of times in context, the y-intercept does not have a whole lot of meaning. We're mostly focused on the slope. And a lot of times you'll see regression equations or formulas that disregard the y-intercept altogether. They try to make the y-intercept 0 if that context fits that. If it makes more sense, we can adapt it to that. But we're really looking for that rate of change. That's the big deal for us in terms of linear regression and correlation. So we're going to try to stay with the same example here, the tapping of the cans, and what we're looking at in the next example is a very bad word when it comes to linear correlation and regression, and it's called extrapolation. Extrapolation means that we would try to predict the amount of soda that would be left for tapping the can for 14 seconds or 20 seconds, right? So this says 60 seconds of tapping. Well, we only gather data that assessed anywhere from 0 to 12 seconds of tapping. So we really ought not try to project something that will be happening outside of that particular window. It would be like looking at, let's say, spelling scores and shoe sizes for elementary students. Well, it would make sense that there be a positive correlation at the elementary school because a fifth grader has bigger feet than a kindergartner and reads on a higher level or has a higher spelling level, for example. But if we try to use that regression equation on adults, shoe size at that point has nothing to do with a person's ability to read or spell. So extrapolation, we want to be wary of that. If we're asked to make a prediction that occurs outside of the range of the data that we've collected, it's really not a good idea. It's kind of an irresponsible way of using that regression equation. Okay. So now we have another new vocabulary word, the residual. Okay. So one thing I want you to keep in mind, this is not on your formula sheet anywhere, but you have to know this. The residual means the actual y value minus a predicted y value. And I think I talked about this a little bit in our other Edpuzzle, understanding R squared, because that's where the residuals come from. So it's a prediction error. All right. So for example, they're asking me for the residual for a can that was tapped 4 seconds and had 260 milliliters of soda in it. So let's see if we can locate that. It's right here. It's almost on the least squares line. Looks like it's pretty close, which means it's going to have a really small residual if we do this correctly. So I need to take the actual amount of soda, which was 260. And I need to subtract from that the predicted amount. So to subtract the predicted amount, remember we need the least squares regression equation. Okay. So the actual amount of soda for this can that was tapped 4 seconds happened to be 260. Now there's other actual amounts. Remember there were several cans that were tapped for 4 seconds, but this particular one had an actual amount of soda equal to 260. Here's my regression equation from previously. We saw that 248.6 plus 2.63, and then we multiply that by our x value, 4 seconds. It was tapped for 4 seconds. So we'll let the calculator do the heavy lifting here and just plug in. So I just plug right into that. I take the actual 260 minus what we will be predicted, and then like we said, it looks like it's a pretty small residual, okay, 0.88 milliliters. Right? That's how much our prediction was off. So think about it. If a residual lives above the least squares line, it means our prediction was too low. If the residual lives below the least squares line, it's going to be negative, and it means our prediction was too high. Okay, so just some important things to think about when we're considering residuals. Okay, so that's just calculating the residual. So one of the things your calculator does every time you do a regression line, regardless of what calculator you have, it automatically stores a list of residuals. But you have to calculate, once you do this command that we've been working with, linreg, okay, L1, L2. The 8384s store it in a list called residual that's in your list. And the nspire has it as well, and you can plot them with the nspire pretty easily. The Desmos will also show you the residual plot as well if you ask it to when you make a regression line. But here's just the list of all my residuals. You notice if I added all these up, all these positive and negative numbers, they're always going to add up to 0. That's a property of the least squares line. And remember, I also said that another property of the least squares line is that x bar, y bar always lives on the least squares line. This point, x bar, y bar, if I take the mean of all the x's and the mean of all the y's, that point is always on my least squares regression line. So here we can see both at the same time, and if you think about this, if I took this line and sort of turned it sideways, you can sort of see what the pattern in the residual plot would be. Generally what we're looking for, if a linear model is a good fit, we want to see kind of no pattern in the residual plot. If I had a least squares model that was, we've talked about this before, that had sort of like a bending shape to it, right? That's kind of curving. And then I try to draw a least squares line. We might have a positive correlation, but then when I go and look at the residuals of this plot, let's think about what the residuals would look like, right? This is my least squares line. So if a point is on that line, it has a residual basically of 0. So like this guy be on here. So if I start here, I have a point below the line, so that's a negative residual. And then another point roughly about the same amount below, and then another one a little bit more below, and another one really far below. And then we start to get a little bit closer to it. Okay, and we sort of have something like this. And then all of a sudden we have a point up above, then we have a point real close to it, and then another one above and another one above. So I'm taking these points and showing what the residuals will look like. When I see a clear pattern in the residual plot, see how this is turning and moving through here? That's a clear pattern in the residual plot. That's something that indicates to me that the linear model might not be a very good fit. Okay, it might be some kind of a curving model, like a exponential or possibly quadratic, something like that. So one of the statistics you're going to see, especially when you see a computer printout, is this S. It's not the slope. It's not the slope of the least squares line. What this is the standard deviation of the residuals. You don't have to be able to calculate this, but you need to be aware of what it means. It's a typical prediction error. Okay? When you see that value S in a computer printout, we're going to see it in a later example, it means it's a typical prediction error. Right? If we use this line to predict the amount of soda that's going to be left in the can after a certain amount of tapping, typically we can expect our estimate to differ from the actual value by about 5 milliliters. Now this is what we looked at on Remote Wednesday. This is our definition or our understanding of R squared. Okay? If we knew nothing about X, right? If we knew nothing about tapping time, we never paid any attention to that, how would we estimate the amount of soda left in the can? Well, we would just take the average amount. And if we did that, these squares represent the amount of error that we have. See how big these residuals are? Okay? Now, these residuals, just like the least squares line, these are positive, these are negative. They'll add up to 0, but this is a lot of error. What happens when we invite tapping time to the party, right? And we plot this line now, instead of just predicting the same number every time, the average, we're going to say, well, if tapping time was 2 or tapping time was 4, we're going to make different predictions for the amount of soda left based on the tapping time. And when we do that, notice that these squares have gotten so much smaller. How much smaller? 85%. So the amount of unexplained error that we had previously that's unaccounted for, we only have 14.6% unaccounted for. That means that we went ahead and explained 85.4% of this error. Okay, that's what R squared means. Okay, it's the percent of variation or percent of change in the y variable. Explained by tapping time. Okay, and that is another definition that we have to commit to memory. What does R squared mean? How do we interpret it? It's not enough to just say it's 85.4% or it's 0.854. We want to say that 85.4% of the change in the amount of soda that's left is explained by tapping time. We want to avoid at all costs thinking that this is some kind of percent reliability of the line. I'll have students say that. The line is 85.4% reliable. That's not true at all. I mean, there's not many points at all that land on this line. You know, if there's, 100 points here, maybe 10 of them land on the line. It's not how reliable the predictions are. It's a measure of how well that line explains the behavior of the amount of soda that's left based on the tapping time. So it's the percent of variation in the y variable that's explained by the x variable, or that's explained by the least squares line, however you want to articulate that. Okay, so here we have a least squares regression line and the residuals side by side. We can see that the line's an appropriate fit because we kind of have a random scatter in the residual plot. We don't see any clear curving, bending pattern in the residual plot. All right, so different data now. We're getting away from the soda tapping. This is the 40-yard sprint times. We have seen this example before, and they're long jumps. So this is a scatter plot for 12 students. They give us the least squares regression equation and then also our residuals. So here it says calculate and most importantly interpret the residual for Christian, who had a sprint time of 7.25 and a long jump time of 110 inches. Let's see if we can locate him on here. 7.25, I'm going to guess he's right here. Right? Does that look about right? 7.25 and 110, that sounds about right. Okay? So before I ever calculate it, I can see that the least squares line prediction for his long jump was too low. Right? It has a positive residual, it was above the line, so the least squares line made a prediction that was too low. But let's go ahead and calculate that residual. Okay? It's his actual long jump time, which was 110, minus the predicted long jump time, which would be 414.79 minus 45.74 times 7.25. And again, we're going to let the calculator do the heavy lifting there for us. I'll just plug that in. Okay, so I enter that, and as we expected, it's the prediction was too high, 26.825. So let's go back and see if we can interpret that. Okay, this is 26.825. Okay, so this means that Christian's actual long jump it was 26.825 inches higher than what was predicted, right? It was predicted to be down here somewhere, maybe in the 80s, but it was actually 110. So 26.825 inches higher than predicted. That's an interpretation. Don't miss that question to interpret it. Don't just calculate these things, okay? Is a linear model appropriate for the data? Let's think. So I've alluded to this before. We look at the residual plot down here, know what we're looking at. A lot of times I'll have students see a residual plot with no scatter plot, and they think they're looking at the actual scatter plot, and they'll say, you know, this model is not appropriate because there's no association between the two variables. So make sure you're paying attention to whether you're looking at the scatter plot of the data or the residual plot. We should be able to go back and forth. Like if I took this here and turned it, 45 degrees counterclockwise, I'd sort of almost get a real look at the residual plot. Remember, the residuals don't go vertical, right? Or not that way, sorry. It's not vertical. Those distances would be vertical to the line like that, okay? So when we make the residual plot, it's not exactly the same, but in general, we should be able to get a good sense of what the residual plot would look like by looking at the original. So since there's no clear pattern in that residual plot, we would be inclined to say that the linear model is appropriate. Remember, R only tells us if the correlation is strong and whether it's positive or negative. It doesn't tell us if it's linear. This residual plot gives us the wisdom to know whether or not the relationship is linear. Okay. Interpret the value of S, 22.38. If we use this line, okay, this line here, to predict long jump based on sprint time, we can expect a typical prediction to differ from the actual long jump by about 22.38 inches. Okay, that's what S means. It's the standard deviation of the residuals. It's a typical prediction. So if we use this least squares regression line to predict long jumps, we can expect our predictions to differ from actual jumps by about 22.38 inches. Okay, that's what our typical prediction means. R squared. Okay, let's look at what the R squared value is, and then we're going to interpret it. So they tell us that R squared is 0.702. I'm going to articulate that as 70.2%. Okay, so 70.2% of the variation or change in long jump is explained by sprint time. Okay, lot of definitions here and terminology to unpack and to commit to memory that you've probably never encountered in a lot of typical math classes, but it's really, very important that we understand how to interpret slope, that we understand how to interpret R and R squared. The standard deviation of the residuals, it's not huge, but you can, I'd say you're like, 60% like 70% likely to see that pop up on an AP exam somewhere. It's important that you be able to interpret that and understand it in a computer printout, okay, if you're doing a regression analysis. Okay, I still remember being a senior in high school and having my teachers tell me, make sure when you go to college, you sit in the front. People that sit up front do better. Again, I think that's one of those situations where somebody might be associating cause with correlation. I think students who generally like to sit closer to the front of the class are more interested. Probably are going to do better anyway. I think if we randomly assign people to seats, that's the only way to do it. My teachers are telling me to go sit in a certain spot in a class. That's my choice. If we randomly assigned students to seats and we found that on average students that sit closer to the front do better, then we'd have a reason for cause, but we'd have to randomly assign that. We can't just say, well, somebody chooses to sit closer to the front, they may be choosing to do other things that make them do better in the class as well. So here we have a typical computer printout. I want to make sure that we can get a regression line off of this. So let's remember what we're doing. We're predicting score, okay, based on the row that they're sitting in. Looks like a negative correlation, but remember what row 1 means that you're closer to the front. So the model would suggest that people sitting closer to the front are scoring higher. So what does the regression equation of the least squares line look like here? Well, first of all, just based on the scatter plot, we know we're trying to predict score. So I put a hat over the score, and that's my starting point. Now I come down here, and this is really what I want to lock in on. The rest of this we'll deal with later on in the course when we do statistical inference. The constant in any regression equation or linear equation is your y-intercept. So we'll throw that in first. We'll go a plus bx form. 85.706, and now my rho, that's my coefficient of rho. Remember, rho is the x variable. The coefficient of the x variable is always your slope, so this would be minus 1.1171 times rho. Notice I don't like to use x or y. If I write y hat and I put x over here, somewhere I need to explain what x and y are. Okay, so be careful if you're going to say y hat equals 85.706 minus 1.1171x, that's fine, but you have to define these. You have to tell me what x and y hat are. Okay, so I just usually write them right in the equation, and then there's no confusion. Everybody knows what the equation, what the purpose of it is. I'm predicting scores based on rows. Okay, and then a couple of typical questions that we've already answered. Interpret the slope. We did this already, right? So for each additional row away from the front, the predicted score or the score is predicted to decrease by negative 1.1171 points, right? So it's a typical interpretation of slope of a least squares line. Find the correlation. To find the correlation, don't pay attention to the r squared adjusted. I don't know why they even give that to us, but r squared is 0.47, so I would have to take 4.7%. I would take 0.047 and take the square root of that, okay? And keep in mind it has to be negative, right? This is a negative slope of a least squares line, so my r value is negative, okay? So let me double back on both of those. Okay, so to summarize what we have here, your slope. For each additional row from the front, the predicted score decreases by 1.1171 points. R, you have to use some wisdom here and know that r has to be negative. Remember, r could be positive or negative based on r squared. We take the square root, and r is clearly negative because the slope of the regression line is negative. And then finally, I look at my residual plot, and I don't see any clear pattern. I don't see anything curving or bending there. So I would say yes, since there is no pattern in the residual plot, the line is appropriate. Is there a lot of error? Is r squared, we only have 4.7% of the change in scores based on row. So sort of like my suspicion, I don't know how much how reliable sitting closer to the front is going to be. I think what's most reliable is that you really care about whatever course it is, and then that's going to probably determine where you want to sit in that class. Okay, and so finally, the last question here, they're giving us some statistics, some one variable statistics. They're giving us the average of the seat location is 4.003. That's the average seat location, or average row rather. And then this is the average score in the class, 81.2. And they also give us a standard deviation. So this could look confusing, but if you take a look at our formula sheet, if you sit for the AP Stats exam, there's two pretty critical formulas on here. The one is for the least squares line. I'm trying to get my highlighter to annotate here. Yep. Not that, just this. Really just these two, if I can circle them up. Not really letting me do it. So I have my equation for the y bar, okay? This would be the y-intercept, a plus b x bar. That's basically you're finding the equation of a line using the slope and a point. We know that x bar, y bar always lives on the least squares equation. So if I wanted to find a, the y-intercept, it would just be y bar minus be x bar. I don't know why they don't just translate it that way for you. But this is probably the real important one, because we can't get to that y-intercept if we don't first get the slope. The slope of the least squares line, and hopefully this makes sense to you, slope has always been defined for you in algebra as change in y over change in x. Well, think about how we're describing or articulating the change in our variables is standard deviation. So we take the standard deviation of y over the standard deviation of x, multiply that by the correlation coefficient, and we have our slope. And then to find the y-intercept, I'll just take y bar minus the slope times x bar. I'll show you what I mean in that example. So the first thing I'm going to do here is to get the slope. Okay. Let's call it b. All right. We want to write this equation: y hat equals a plus bx. It's basically what I'm attempting to do here. Okay. And I know that this point is on the line. This is a classic Algebra 1 problem. Write the equation of a line given the slope and a point. So we don't have the slope outright, but I'll go ahead and get it. I take the correlation coefficient, negative 2.18, and I multiply that by the change in y, which is 10.135, over the change in x. That's my slope. Change in y over change in x, 1.974. That's going to give me my slope. So we'll take their word for it. They said it's negative 0.218. We got negative 0.217, but we only had the 0.047 to go by. So they probably have a little bit more accurate rendering. This looks like it's going to be wrong. I got to fix that. Not 1,974, 1.974. So this is going to be my slope. I get negative 1.119. We'll go to 3 decimal places. Okay, and now I know that x bar, y bar lives on the line, so if I were to plug that point in and I wanted to get a, I know that a would just be y bar minus b x bar, and they give me y bar and x bar. I can plug into them. So a is going to be 81.2 minus my slope, which, keep in mind, is negative, so let's be careful there, times x bar, which is 4.0033. So I plug that in. For slope, for y-intercept, I get 85.713. So we're going to say score predicted equals 85.713 minus 1.119 times the row. Right? So notice I keep everything in context, predicted score and row, so there's no confusion about what this least squares line is predicting.